We would like to determine if the sequence converges or diverges. Our sequence is C sub n equals n squared over 2 to the n plus I times the nth root of n squared plus 1. So our sequence has a real part and an imaginary part. We could think of our sequence as being of the form an plus I times bn then, where an and bn are real sequences. So if an converges to a and bn converges to b, then that means that cn will converge to a plus ib. So we're basically going to look at these two real sequences and find their limits. So we want the limit as n goes to infinity of n squared over 2 to the n, and we want the limit as n goes to infinity of the nth root of n squared plus 1. So we'll talk about these intuitively, and then we'll do them in rigorous detail. So intuitively, this n squared is a polynomial, and on the bottom 2 to the n is an exponential. As n grows, the exponential will grow faster than the polynomial, and so this limit should be 0. And we can use L'Hopital's rule twice to verify that. And let's do a little bit of numerical investigation first, just to see this growth. N squared versus 2 to the n. If n is 10, then n squared is 100, and 2 to the n is 1024. So we can see already that 2 to the n is 10 times bigger than n squared. And if we make n equal to 100, the situation is even more dramatic. N squared is equal to 10,000, which is 10 to the 4th. And 2 to the n, 2 to the 100, is bigger than 10 to the 30th. So 10 to the 30th is astronomically large versus 10,000. So we can see that the exponential is going to be much larger than the polynomial. L'Hopital's rule gives us that this limit, which is infinity over infinity, equals by L'Hopital's rule. The limit as n goes to infinity of take the derivative. We'll just leave the variable as n and take derivative with respect to n. So 2n, and the derivative of 2 to the n is 2 to the n times the log of 2. Now this is still infinity over infinity because 2 times n goes to infinity. So we do it one more time to get rid of the n in the numerator here, and we get the limit of 2 over, and the derivative is on the bottom is 2 to the n log 2 times log 2. And the numerator is a constant, the denominator still goes to infinity, 2 over infinity, and the limit is 0. So the a is 0. So our limit is going to be 0 plus I times whatever bn goes to, assuming that it converges. So let's see, here's the bn's here. The nth root of n squared plus 1. The nth root of n is known to go to 1, and we'll show why essentially we'll use the same technique that would show this to get this one formally. But let's just do it intuitively. If we know that the nth root of n goes to 1, then the nth root of n squared would go to the nth root of n squared, which is just 1. And then adding 1 inside the radical isn't going to change things. So this still goes to 1. Now, showing this one is a little bit complicated. We consider this is n squared plus 1 to the power 1 over n. And in order to use L'Hopital's rule, we have to rewrite this as e to the power log of n squared plus 1 to the power 1 over n. And then we can use a log property to bring down the 1 over n, so that it's e to the power log of n squared plus 1 times 1 over n, or over n. So we have to calculate this limit and then do e to that power. So the limit as n goes to infinity of log of n squared plus 1 over n. This is infinity over infinity, so we can use L'Hopital's rule and the derivative on the bottom is just 1, so I'm not going to write that. And the derivative on the top is chain rule 1 over n squared plus 1 times 2n. And now this is a basic calculus 1 limit polynomial over polynomial. The degree on the bottom is bigger, so this one's bottom heavy. And so the limit is 0. Of course, we could use L'Hopital's rule one more time and see that as well. But at this stage, hopefully we recognize that one. So this one is 0, and so this one is e to the 0, which is 1. So the b is 1, and the cn converges to 0 plus I times 1, or just I. So our sequence n squared over 2 to the n plus I times the nth root of n squared plus 1. This sequence converges to I as n goes to infinity.